Hello everyone, I am Dr.B.Krishnaveni, Assistant Professor, Department of Mathematics, Aditya University. Today we are going to discuss about applications of multiple integrals. That is, what the applications of multiple integrals here is, we are going to know what about areas and volumes to find these two using multiple integrals. So hence the learning outcome of today's lecture is student will be able to apply multiple integrals to find areas and volumes. So now first let's discuss about the area using double integrals. Consider the area enclosed by the curve y is equal to f of x, y is equal to g of x is equal to a, x is equal to b in the xy plane. The area of the region R bounded by the given curve is given by a is equal to double integral over r dx dy or double integral over r dy dx. So which can also be written as integral x is equal to a to b, y is equal to f of x g of x dy dx. And if the region is represented through polar coordinates, then the area is given by a is equal to double integral over r dr d theta. So here we are going to learn about to find the area using double integrals. So one in Cartesian, the other in polar. So to find the area in the Cartesian form, so in that if you are taking a region R bounded by the curve, then it is given by a is equal to double integral over r dx dy or double integral over r dy dx. So depends upon the limits we have taken in the question, we will take either dx dy or dy dx. Now if the region is represented through polar coordinates means the area is given by double integral over r dr d theta. So now let's see the question on this. Evaluate the area enclosed by the parabolas x square is equal to y and y square is equal to x. So first let's get the area bounded by these two curves. So one is parabola, the symmetrical to x axis, the other is the parabola symmetrical to y axis. X square is equal to y, which is symmetrical to y axis, and y square is equal to x, which is symmetrical to x axis. Now the area bounded by these two curves, this is the dotted area which is bounded by these two curves. So now to find the points of intersection, as we already know, substitute one curve into another curve. So let us substitute x square is equal to y and y is equal to x square in the second curve, then it will become y square, that is x power 4 is equal to x. Solving this equation, we got x is equal to 0, y is equal to 0, and the corresponding y values by taking the equation, any of the equation, x is 0 means y is 0, and if substitute x is equal to 1, we are getting y is equal to 1. Hence the points of intersections are given by 0, 0 and 1, 1. Now coming to the limits. To get the limits, we already discussed how to find the limits in the region, either by using horizontal strip or by using vertical strip. So in this question, let us consider horizontal strip. So then we'll get x limits along the strip from left to right. So left is touching the curve, y square is equal to x means x is equal to y square. To right is touching the curve, x square is equal to y, which gives x is equal to root y. Now the corresponding y limits are given on y axis in the region of integration. So this is the region of integration along y axis. Here it is 0, 0, and this point will be, here point of intersection 1, 1 means this point will be 0, 1, and y varies from 0 to 1. So now taking into this limits, we need to find the area enclosed by these parabolas, and we know that area is given by double integral over r dx dy, and here the x limits are from y square to root y is equal to 0 to 1, hence the order must be dx dy. Since we have taken horizontal strip, that's what we got x limits as variables. Now let's do first with respect to x, keeping y constant. So integral dx is x, substituting the limits upper limit minus lower limit, that is a root y minus y square. Now for this integration with respect to y between the limits 0 to 1. So y root y can be written as y power 1 by 2, and y power 1 by 2 integration is y power 1 by 2 plus 1 by 2 plus 1. So which gives y power 3 by 2 by 3 by 2 minus y square integration y cube by 3. The limits y is equal to 0 to 1. Substitute the upper limit So 1 by 3 by 2 is a 2 by 3 minus 1 by 3, and lower limit is a 0. 2 by 3 minus 1 by 3 is equal to 1 by 3. So this gives the area bounded by this parabolas. Now the next question, find the area of the plate in the form of quadrant of the ellipse x square by a square plus y square by b square is equal to 1. And here the curve is the ellipse x square by a square plus y square by b square is equal to 1 in the form of quadrant. So that means you can see the area, shaded area in the figure is nothing but the area which we have to calculate. So now to find out this, first let's find out the limits. For that, in this question let us consider vertical strip. So vertical strip means first we will get y limits along the strip from down to up. So down x axis means y0, up is the ellipse x square by y square plus y square by b square is equal to 1. From this what is y is equal to? If you simplify this to find y, so we will get b by a root of a square minus x square. So now the x limits in the region of integration, that is from this point to this point. Since it is an ellipse, we know that the point here it is x0, here it is 0b. So ultimately it is 0, 0, a0. Hence the x limits are from x is equal to 0 to x is equal to a. So we know that area is equal to double integral over r dx dy. That is x is equal to 0 to a, y is equal to 0 to b by a root of a square minus x square dy dx. So now integral dy is a y. Substituting the y limits, upper limit b by a root of a square minus x square, lower limit is 0. So now b by you can take outside the integration. Now do integration with respect to x. So it is in the form of a root of a square minus x square, and we know what is an integration for this, that is x by 2 root of a square minus x square plus a square by 2 sin inverse x by a. Now x limits are from 0 to a. On substituting the limits x is equal to a, the first term becomes a 0 and the second term a square by 2 sin inverse a cancel and sin inverse 1, and if you substitute lower limit x is 0 means both 0, so that's what lower limit is 0. So finally you got this is equal to b by a into a square by 2 into sin inverse 1. So this gives the area for the given curve, that is the ellipse of the quadrant. Now next is using double integrals, find the area of cardioid r is equal to a into 1 minus cos theta. So the cardioid r is equal to a into 1 minus cos theta is shown in figure. This is the cardioid r is equal to a into 1 minus cos theta. And the area, you need to find out the area of this cardioid, so which is the shaded area. Now since here it is, you can easily identify the area is in polar coordinates. So hence we need to find out the area in polar coordinates, which is given by double integral over r dr d theta. So for that we need r limits and theta limits. So hence let's take the strip. In the polar form we will take the strip in this point from the initial point on the curve. So the initial point is this, that is r is equal to 0 to the cardioid. So that means r limits are from 0 to a into 1 minus cos theta. And to cover this area, it has to travel from this entire region. This strip has to travel this entire region. So to cover this, let us take the upper part. That is, here it is a theta is equal to 0 to theta is equal to pi. For that 2 times, exactly it is bisecting the entire region. So hence we can find out the upper part region by means of a theta, that is theta 0 to theta is equal to pi. If you apply 2 into of that integration means you will get the total area of that cardioid. So hence this area will be equal to 2 into theta is equal to 0 to pi, r is equal to 0 to a into 1 minus cos theta r dr d theta, which is equal to 2 into 0 to pi, integral 0 to pi, integral r is r square by 2, the limits are from 0 to a into 1 minus cos theta. Substitute the upper limits here 2 to cancel. So r square it is, that is a into 1 minus cos theta whole square d theta. Simplify and do integration with respect to theta. So then we are getting this is 4a square 0 to pi sin power 4 theta by 2 d theta, which is equal to 4a square integral 0 to pi by 2. Sine power 4 theta, you can take theta by 2 is a 5, means you are getting that is equal to sine power 4 pi 2 d pi. So by means of the expansion, integral 0 to pi by 2 sine power n theta d theta, and depends upon the n value if it is even or if it is odd. Here it is n is equal to 4, which is even. So apply the formula n minus 1 by n, n minus 3 by n minus 2. So on 1 by 2 into pi by 2. So now substituting n is equal to 4 in this, 4 minus 1 is 3 by 4, 4 minus 3 is 1, 1 by 2, that means you are getting this into pi by 2. So which gives 8a square 3 by 4 1 by 2 pi by 2, that will be equal to 3 pi a square by 2. So this gives the area of the given cardiad. Now the next is finding the area which is inside the cardiad. R is equal to a into 1 plus cos theta, and outside the circle r is equal to e. So for this, let take the graph correspondingly so that we can find out the region of area which we need to calculate. The first is cardiad r is equal to a into 1 minus cos theta. This is the cardiad. And the circle r is equal to a means it is the circle r is equal to e. So it is cardiad, that means this point is a, let us represent with a and given by 2a comma 0, and here it is exactly a comma 0, hence we need to draw the circle in this form. So now we need to find out the area which is inside the cardiad. So it is inside, and outside this is the circle, we need to exclude this part. So the remaining part you need to find out the area, so which is the dotted area in the figure. So this is the area we need to find out. So for that, first we need to find limits. Let us draw a strip in this form, and now the area along the strip from this point to this point we need to consider, and this point of r is equal to a, and at this point r is a cardiad, that is r is equal to a into 1 plus cos theta. So now the area, so this part is the area. To find out this entire area, let us find out the upper part of area, and 2 into of that area gives the entire area. So that's what here theta, what theta will be equal to 0 to theta is equal to pi by 2, which 2 into, okay. So that means first of all, what is the area in the polar form is a is equal to double integral over r dr d theta, which is equal to, so now r limits r is equal to a into a into 1 plus cos theta, and to find out the upper part, theta limits are from 0 to pi by 2. Since to find out the entire area, we need to take 2 into 0 to pi by 2, and the formula r dr d theta. So let's find out the integration. Now first with respect to r square by 2 between the limits, substituting the upper limit, lower limit, on cancelling here 2. Thereafter do integration, simplify and do the integration with respect to theta. So on simplification, you got this 1 plus cos theta whole square minus 1, which is equal to 2 cos theta plus cos square theta. And here cos square theta can be written as 1 plus cos 2 theta by 2. And now this is equal to, now do integration with respect to theta. 2 into cos theta integration is sin theta. And 1 by 2 you can take outside, integral d theta is theta. Cos 2 theta integration is sin 2 theta by 2. Now the theta limits are from 0 to pi by 2. Substitute the upper limit, theta is equal to pi by 2, the lower limit theta is equal to 0. If you substitute the upper limit theta pi by 2 means 2 into sin pi by 2, which is 2, plus 1 by 2 into pi by 2 plus sin 2 pi by 2, that which will become sin pi, that is equal to 0, right. So what the lower limit is, if you substitute theta is equal to 0 means the total lower limit is 0. So simplify this, a square into 2 plus pi by 4, which is equal to a square by 4 into pi plus 8. So this all about finding the area using double integration. Now the next application is finding the volume using double integral. So now for this, let us consider z is equal to f of x comma y be the surface in xy plane. Then what volume will be equal to? That is v is equal to double integral z dx dy, where z is the surface f of x comma y. So now the same in polar coordinates, the volume is given by double integral f r comma theta r dr d theta. So now let us discuss the question on this. Find the volume bounded by the cylinder x square plus y square is equal to 4, y plus z is equal to 4 and z is equal to 0. So now the question on this. So find the volume bounded by the cylinder x square plus y square is equal to 4, y plus z is equal to 4 and z is equal to 0. So now here given the equation of the cylinder x square plus y square is equal to 4, z is equal to 0. So now from first you got x is equal to plus or minus root of 4 square 4 minus y square, and if x is 0 in that equation, what we get, y is equal to y square is equal to 4, that means y is equal to plus or minus 2. And the equation of the plane given by y plus z is equal to 4. From this what z is equal to 4 minus y. So clearly what are x limits are minus root of 4 minus y square to root of 4 minus y square, and y limits here it is there, that is minus 2 to 2, and here what z is equal to 4 minus y. By taking all this we need to find out the volume bounded by this cylinder. And what the required volume is given by, the given formula is double integral over z dx dy. So where y is from minus 2 to 2, x is from minus root of 4 minus y square to root of 4 minus y square, and z, just now we got what is z is equal to 4 minus y dx dy. So hence since x limits are variables, need to do first with respect to x, then with respect to y, and this is equal to 2 into integral y is equal to minus 2 to 2, x is equal to 0 to root of 4 minus y square 4 minus y dx dy. So instead of y is equal to minus 2 to 2, we can find out 2 into integral 0 to, we can find out this. So which is equal to 2 into integral y is equal to minus 2 to 2, 4 minus y, what is integral ds is x, substitute the upper limit and lower limit. So the upper limit is root of 4 minus y square, the lower limit is 0. So next we need to perform this. First we have to simplify. So the first term becomes 2 into 4 into root of 4 minus y square, or the second term is minus y into root of 4 minus y square dy. So now if we consider this, we have taken the first term only because the second term is an odd function and the integral from minus 2 to 2 becomes 0. So now this 4 into 2 is 8, y is equal to minus 2 to 2 root of 4 minus y square dy. Since now the first part is even, we can write this as 2 into integral y is equal to 0 to 2 root of 4 minus y square dy. So now it is exact in the form of a root of a square minus x square dx. Now what is an integration for this is x by 2 root of x square minus a square plus a square by 2 sin inverse x by a. Now by taking that formula, the above integration can be written as y root of 4 minus y square by 2 plus 4 by 2 sin inverse y by 2. Finally substitute the y limits here. What are y limits? Y limits are from 0 to 2. Substituting the upper limit to 2, 2 into root of 4 minus 4 becomes 0, 4 by 2 sin inverse 2 by 2 is sin inverse 1, and what about lower limit is y into something, that means 0 into something is 0, sin inverse 0 0, the lower limit is 0, and this will be equal to 2 into 16 is 32, sin inverse 1 which is pi by 2, that is equal to 16 pi. So this is the way you can find out the volume of the given region. So hence in this lecture, we got an idea about the application of multiple integrals which were used to find out the area and the volume of the given regions. Thank you.